The following content is provided by MIT OpenCourseWare under a Creative Commons license. Additional information about our license and MIT OpenCourseWare in general is available at ocw.mit.edu.
All right, I'm going to start with Friday's lecture notes because there was a significant amount on them that I hadn't finished up yet. We had finally gotten to the point where we were talking about what does a wave function mean? What is the physical significance of it? How does it actually represent the presence of an electron? And what we saw was that the physically significant representation of the wave function, if you have some wave function psi labeled by three quantum numbers n, l, and m, and of course it's a function of r, theta, and phi, the physically significant quantity was this wave function squared. That wave function squared that was interpreted as a probability density. So the wave function squared has units. It has units of inverse volume. It's a density. It's a probability per unit volume. Now, as an aside, because someone asked me, I should tell you that the more comprehensive definition of the probability density is psi, not squared, but psi times psi star, where psi star is the complex conjugate. Because it turns out that some wave functions are imaginary functions. Right? And so if you took an imaginary function and squared it, well, then you'd still get an imaginary function after it. And then it's hard to interpret a imaginary function as a probability density. And so the more comprehensive definition is psi times psi star, where psi star is the complex conjugate of psi. And when you multiply psi by psi star, if psi is a complex function, well, then you get a real function. Okay? So this is the more comprehensive definition of the probability density. It's psi times psi star. We won't use that. I just wanted to let you know about it. Okay. So probability density. But not only do we want to know something about the probability density, we also want to know something about the probability, all right, of finding the electron some distance away from the nucleus. And to do that, what we were talking about is this quantity, this radial distribution, the radial probability distribution. And what that is the probability of finding an electron in a spherical shell of radius r and distance or thickness dr. So for example, if this gray portion here represented the probability density of the 1s wave function in our dot density diagram, remember we squared the wave function, got the probability density, and then represented it with a dot density diagram where the density of the dots was proportional to the value of the wave function squared. And in the case of the 1s wave function, we saw that the probability density was largest right at r equals 0, and that it exponentially decayed isotropically. It exponentially decayed in all directions uniformly. All right, so that's what that gray part represents. But now, this blue here, the blue is my spherical shell. It has a radius r, right? And it has a thickness here, dr. And the radial probability distribution is asking what is the probability of finding the electron in this spherical shell and that spherical shell has a thickness dr. All right? So another way to ask that is the probability of finding the electron between r and r plus dr. That's what we want to know, and that's what the radial probability distribution tells us. All right, now, how do you get a value out of that? How do you actually calculate the radial probability? Well, to do that, what we have to know is this volume here of the spherical shell. All right, the volume of the spherical shell is just the surface area of that spherical shell, 4 pi r squared, and the volume is times this thickness, that thickness dr. It's a very thin shell. It's an infinitesimally thin shell of thickness dr. Okay, well, if we know that volume, then what we can do is we take our probability density, psi squared, which has units of probability per unit volume, and we're multiplying it here by our unit volume. The unit volumes cancel, and we're left with a probability. So that's our probability of finding that electron in a shell of radius r and a thickness dr. Okay, so let's look at the result of calculating the radial probability distribution for the 1s wave function. So what did I do? I took psi squared for the 1s wave function, and then I multiplied at some value of r, and then I multiplied it by 4 pi r squared dr, and I did that for many different values of r, and I plotted the result here. So that's what that radial probability is as a function of r. Okay. Well, the first thing that you see is that the most probable value of r, or the value of r where the electron has the highest probability of being, is at this value a naught. The most probable value of r is this value a naught. A naught is what we call the Bohr radius. And today, in a moment or so, I'll tell you why it's called the Bohr radius. It has a numerical value of 0.529 angstroms. Okay? And so it is most likely that the electron is about a half an angstrom away from the nucleus, making then the diameter of the hydrogen atom on the average a little bit over 1 angstrom. All right? That's how we think about the size of a hydrogen atom, is to take this most probable value of r and double it to get the diameter. So the most probable value of r, or the most probable distance of the electron from the nucleus, is half an angstrom away. The most probable distance of the electron from the nucleus is not r equal to 0. Because look, the radial probability here is 0 at r equals 0. Hey, that seems a little strange, because the other day we plotted the probability density for the 1s wave function. And when we did that, we saw that, so here's psi 100 squared, right, versus r. What we saw is that the probability density was some maximum value at r equals 0, and that it decayed with increasing r, exponentially decayed with increasing r, and that is the case. Probability density for the s wave functions is a maximum at r equals 0. But the radial probability here is actually 0 at r equals 0. Why? Because look at, how we define that radial probability here, right? It is psi squared times this volume element. Our volume element is the spherical shell. And at r equals 0, the spherical shell goes to a volume of 0. So our radial probability here is equal to 0 at r equals 0. Okay? That is really important, that you understand that this radial probability here is always going to be 0 at r equals 0 for all of the wave functions that we're going to look at. Okay? Okay. Now, and we'll talk about this a little bit more, the fact that the electron is about a half an angstrom away from the nucleus. But before I do that, I also just want to point out that in your textbook, and sometimes in the notes, that sometimes that radial probability is actually written as the following. It's written as this r squared, the distance variable, times the radial part of the wave function. That's the radial part. We talked about the radial and the angular part last time. The radial part squared. And the radial part is labeled only by two quantum numbers, n and l. And so for the 1s, that's n equal 1, l equals 0. Where does this come from? Well, let me just emphasize or to explain where this comes from. This radial probability distribution here, we said for the s wave functions was psi squared. You could take psi squared, probability density, and multiply it by this unit volume, or the volume of the shell, 4 pi r squared dr. All right? Let's write that out again, but write it out now so that we write out psi squared in terms of the radial part and the angular part. Remember we said last time for the 1s wave, for the hydrogen atom wave functions, that psi was always a product of a factor only in r, which was the radial part, and a factor only in theta and phi, which are the angular parts. All right? Now, what you also have to remember in looking at this is that that angular part for the 1s wave functions, that angular part for 1s, 2s, 3s, all s wave functions, that angular part was equal to 1 over 4 pi to the 1/2. All right? So if you square that, you're going to get 1 over 4 pi, and therefore the 4 pi's here are going to cancel for the 1s wave functions. And what you're going to have left is this r squared times just the radial part, dr. Okay? So that's why the axis, the y-axis in your book, is sometimes labeled this way for the radial probability distribution. But this is also important because if you were calculating the radial probability distribution function for something other than an s wave function, the way you would do it is to take just the radial part of that wave function times r squared, or just the radial part of that wave function evaluated at that value of r, times r squared dr. All right? You could not, for the other wave functions, take psi squared times 4 pi r squared dr. And that's because the angular part in the other, for the other wave functions that aren't spherically symmetric, that angular part isn't 1 over isn't the square root of 1 over 4 pi. All right, so this is a broader definition for what the radial probability distribution function is. Okay, it just works out in the case for the s wave functions, these 4 pi's cancel, and so you can write the radial probability for the s wave functions like that. Okay, so that's just some definitions. Okay, but I want to talk some more about this, this radial probability distribution function here for the 1s wave function. I want to talk about it and also to explain why A0 is called the Bohr radius. And the reason for that is the following. Nucleus discovered in 1911, electron known before that. And Schrodinger didn't write down his wave equation until 1926. And in between that, 1911 to 1926, the scientific community was really working very hard to try to understand the structure of the atom. And we saw how the classical ideas predicted it would live a whopping 10 to the minus 10 seconds. And one of the people who were working on that problem was Niels Bohr. And in 1919, Niels Bohr, he of course realized that, hey, classical physics fails this kind of planetary model for the atom, where you put the nucleus in the center and the electron is going around that nucleus with some fixed orbit. We'll call it R. Well, he knew that that wasn't going to work, that those classical ideas would predict this would plummet into the nucleus in 10 to the minus 10 seconds. But he said, hey, obviously that doesn't happen, so let me just forget classical physics at the moment. And then what he did is to impose some quantization on this classical model for the hydrogen atom. And the reason he got this idea of quantization is because he already knew the hydrogen atom emission spectrum. He knew that in the hydrogen atom emission spectrum, that light of only certain frequencies was emitted. That is, there was some idea that there's something about this hydrogen atom that's quantized. All right? So he said, well, okay, let me just ignore classical physics for a moment. Let me give this a circular orbit, but let me quantize something about this hydrogen atom. And in particular, what he went and did is he quantized the angular momentum of that electron. He kind of just pasted the quantization onto a classical model for the atom because he's trying to work toward explaining what the observations were. When he pasted that model onto, or when he pasted that quantization onto this classical model, he was able to calculate a value of R. And that value of R is what we call the Bohr radius A0. All right, and has the value 0.529 angstroms. All right, that came out of it. And if you look then at what you would predict for the, or if you calculate the radial probability distribution function for this model, which is called the Bohr atom. Well, the radial probability distribution function for this Bohr atom would be one where that radial probability is 1 right here at R equal A0. Okay? In Bohr's model, the electron had a well-defined, precise orbit. The value of R at which it went around the nucleus was given by A0. We knew exactly, or he knew exactly where the electron was in his model. This kind of model, which is this classical model really, is what we call deterministic. It's deterministic because we know exactly where the particle, in this case the electron, is. Right? I want you to contrast it with the quantum mechanical result from the Schrodinger equation. What you see in the quantum mechanical result is that we don't really know where the electron is, so to speak. The best we can tell you is a probability of finding the electron at some value R to R plus dr. That's the best we can do because quantum mechanics is non-deterministic. There is a limit to which we can know the position of a particle. That limit is given by something called the uncertainty principle. The uncertainty principle is not something that we are going to discuss, but the uncertainty principle tells us that there's a limit to which we can know both the position and the momentum of a particle. Right? And that is the basis for why here we have a probability distribution in probability distribution in knowing sort of where the electron is. We don't exactly know where the electron is here. Okay? This is a classical model on which Bohr just kind of pasted the quantization of the angular momentum of the electron onto it. In the case of the Schrodinger equation, the quantization drops out when you solve the differential equation. It comes out of the equations naturally. We didn't paste it onto it. We didn't make an ad hoc kind of a representation. All right? So that's the big difference here between quantum mechanics and classical mechanics. In quantum mechanics, I can only tell you about a probability. I can't tell you exactly where the particle is going to be. Okay? Questions on that? Okay. But anyway, this value A naught, that's why it's called the Bohr radius. And then it turns out, quantum mechanically, that this value of R, the most probable value of R, is in fact exactly A naught. Okay? In a sense, Bohr was pretty lucky, and this is kind of an accident that he got A naught out of this, and it has to do with the actual form of the Coulomb interaction. Okay? All right. But of course, this doesn't work for anything else other than a hydrogen atom, whereas the Schrodinger equation, as we're going to see in a moment, is applicable to all the atoms that we know about. Okay. So that's the radial probability distribution function for the 1s atom, for the 1s state. We want to take a look at the radial probability distribution for 2s and for 3s. So let me plot those, and you can actually put these lights on here. Yeah, that's okay. I'm gonna use this board for a moment. So here's the radial probability distribution function. I can write it as little r times r to 0 of r squared, or rpd. This is for 2s versus r. All right? And when I do that, I get a function that looks like this. And if I evaluated here, what is this value of r at which the probability is a maximum? Well, this most probable value of r is 6a naught. Hey, look at that. The most probable value of r for 1s was a naught. In the case of the 2s state here, the electron, the most probable value is 6a naught, 6 times as far from the nucleus. So if you have a hydrogen atom in the first excited state, in a sense, that hydrogen atom is bigger. It's bigger in the sense that the probability of you finding the electron at a larger distance away from the nucleus is larger. Okay? And that, in general, is the case. The radial probability distribution here also reflects the radial node that we talked about last time. That radial node is R equal to A naught. Radial node is the value of R that makes your wave function go to 0. Mm-hmm. Notice, again, that this radial probability distribution function right here is 0 at R equals 0. This is not a node. This is not a radial node. This is a consequence right here, right, of our definition for the radial probability. Our volume element has gone to 0. So R equals 0 is never a radial node in any wave function. Okay? All right, what about 3s? Well, let's plot 3s. So here's 3s. This is the radial probability distribution. I take psi for 3s, cube it, square it, multiply by 4 pi r squared dr, and do so for all the values of r, and I'm going to get something that looks like this. And now, this most probable value of r here for the 3s wave function is equal to 11.468 A naught. So for the second excited state of a hydrogen atom, right? For that second excited state, that electron on the average is 11.5 times farther out from the nucleus than it is in the case of the 1s state right here. Okay? So again, for that second excited state, that hydrogen atom is bigger in a sense, in the sense that the probability of it being farther away from the nucleus is larger. That radial probability distribution of the 3s also reflects the 2 radial nodes in the 3s wave function. The radial nodes are at 1.9 A naught here and 7.1 A naught. And again, the value here at r equals 0, hey, that's not a radial node. Okay. But now, as you look at this, it's tempting to ask the following question. You might want to ask that, say, if the electron can be at these values of r, and it can be at these values of r, and it can be at these values of r, how does the electron actually get from here to here to here if right at r equal 1.9 A naught and 7.1 A naught, the probability is equal to 0? Well, you might say, well, you know, maybe this probability isn't exactly 0. It's something small. But, hey, I'm telling you that it's 0. It's goose egg. It's zilch, zippo, nada, cipher, nix, naught. Anybody else got another name? No. Okay, it is nothing. It is 0. Okay? So, how do you answer that question? Well, turns out, of course, that that isn't an appropriate question. And the reason it isn't is because that question is asked in the framework of classical mechanics. When you ask, how does a particle get from one place to another, you're asking about a trajectory. You're asking about a path. A particle's over here, then it's over here, it is here. How does it get from one place to another? And in quantum mechanics, we don't have the concept of trajectories. And instead, what we have to think of is the electron as a wave. And we already know that a wave can have amplitude simultaneously at many different positions. And so it has simultaneous amplitude or probability here, here, and here, all at the same time. Okay? We can't talk about trajectories anymore. And that all, again, ties into the uncertainty principle. All right? Our inability to know exactly the position and the momentum of a particle at any given instance. All right? The best we can tell you is a probability. All right? So we got to change the way we think about electrons. You can't cast them in the framework of your everyday world. This is part of our world, but you have to go do a specific type of experiment to see this part of the world, right? So that's why it seems so strange to you, because it's not part of your everyday experience. But this world works with different rules that you really do have to accept, that it just works differently. Okay? Okay, questions? Okay. Well, so now I'm going to stop talking about the S-wave functions, and we're going to move on and talk about the P-wave functions. With the S-wave functions, we talked about the significance of the wave function, probability density, radial probability distribution. We talked about what a radial node was. So now it's time to move on to the P-wave functions. And the P-wave functions, of course, are not spherically symmetric. And to represent them, we're going to do our dot density diagram again. So we're going to take the wave function, and we're going to square it to get the probability density, and then plot that probability density as a density of dots. So where the dots are most dense, well, that means the highest probability density. All right? So here's the result for the PZ wave function. It's PZ because you can see the highest probability here is along the z-axis. It's symmetric along the z-axis. All right. Here's the probability density for the PX wave function. You can see that the probability density is greatest along the x-axis. It's symmetric along the x-axis. And if you look really carefully, you can see that there's no probability density in the YZ plane for the PX wave function. And over here, if you look carefully, you can see that there's no probability density in the XY plane for the PZ wave function. And here's the PY wave function, the probability density of it. Probability density is concentrated along the y-axis. It's symmetric along the y-axis. And if you look very carefully, there's no probability density here in the XZ plane. Okay, well, the fact that there's no probability density here in the XY plane in the case of PZ indicates that we have an angular node. An angular node at theta equal 90 degrees. An angular node is the same thing as a radial node in the sense that it's the value of the angle that makes the wave function be equal to 0. So here's the wave function for PZ. You can see that when theta is equal to 0, this wave function is going to be equal to 0. All right, so an angular node is a value of theta or phi that makes the wave function be 0. And the consequence then is that we have a nodal plane, because everywhere on the xy plane, everywhere on that plane, theta is equal to 90 degrees. Okay? For the px wave function, the value of the angle that gives you that nodal plane is phi equal 90. Phi equal 90, that means everywhere in the yz plane, all right? Everywhere in the yz plane is phi equal to 90. And in the case of py, when phi is equal to 0, well, that is everywhere in the xz plane. Everywhere in the xz plane, phi is equal to 0. So that's the angular nodes. So in general, and this is something that you do have to know. In general, an orbital has n-1 total nodes. And what I mean by total nodes is angular plus radial nodes. The number of angular nodes is given by this quantity, L. The quantum number L that labels your wave function always gives you the number of angular nodes. And therefore, if n-1 is the total and L is the number of angular, well, then the number of radial nodes is n-1 minus L. All right? This is something that you do have to know. So if I give you a wave function and ask you how many radial and angular nodes it has, You need to be able to calculate that, and vice versa. Sometimes I will tell you a function has 3 radial nodes and 6 or 7 angular nodes or something. What is the wave function? Okay? So we go both ways. Okay. Well, I also want to take a look at the radial probability distribution functions for the P wave functions. We looked at it for the S wave functions already, and I actually want to contrast the radial probability distribution, say, for 2P, here it is, with that of 2S that we looked at a moment ago. Remember, how do you get the radial probability distribution function here for 2P is the radial part of the 2P wave function times r squared dr. Gives me the probability of finding the electron distance between r and r plus dr. And again, what you see is that at r is equal to 0, hey, that's 0. Okay? That's not a radial node. But what I really want to point out here is that the most probable value of r for the 2P wave function is actually smaller than it is for the 2S wave function. That is, it is more likely for the electron in a 2P state to be a little closer in to the nucleus than it is for the 2S state. All right? So in general, as you increase the angular momentum quantum number, the most probable value of r gets smaller for the same value of n. Similarly, here's the 3S radial probability distribution function that we looked at. Here's the radial probability distribution for 3P. Now with the 3P, you can see the value of the radial node. You can see the radial probability distribution reflects a radial node here. All right? And here's the radial probability distribution function for 3D. We didn't look at the probability density of 3D. You'll do that with Professor Cummins when you talk about transition metals. But here I just drew in the radial probability distribution for 3D. But the point, again, I want to make is here's the most probable value of r for 3S. Here it is for 3P. Here it is for 3D. Hey, again, the most probable value for 3D is smaller than it is for 3P, than it is for 3S. Again, as you increase the angular momentum quantum number, that most probable value gets smaller. However, ironically, if you actually look at the probability of the electron being very, very close to the nucleus, that probability is only significant for the S wave functions. Because look at the 3S wave function. Here you see that you really do have some probability very close to the nucleus. You don't see that in the 3P wave function. You certainly don't see that in the 3D wave function. And again, in the S wave function, 2S, you have some significant probability of the electron being really close to the nucleus in 2S, but you don't in 2P. All right? That's important. All right? That's important, and it seems in contradiction to the fact that on the average, the most probable value of r gets smaller as L gets larger. These two facts that look contradictory are important. They dictate the behavior of atoms. So these two facts seem like kind of loose threads at the moment, in the sense that you're probably wondering why I'm telling you what I'm telling you. But we're going to use that information in a few days. All right? So in a few days, you'll see really the significance of this plot. And this plot will be an important one for you to refer back to. All right? Yes?
If an electron is farther out from the center, does it necessarily have more energy? And secondly, in our simplified high school models, we always drew the P is farther out than the S. Did they average it? Did they average it to probability P?
Probably. I'm not exactly sure the picture that you drew in high school. But yes, if the electron in general is further out from the nucleus, that's a higher energy state. The electron is less strongly bound, right? As we're going to see in the multi-electron atoms here.
So in the homework, we simplified things when we had to just plug in 3, regardless of whether it's 3s or 3p or 3d.
Oh, no, for the hydrogen atom, no. Okay, let me explain that. For the hydrogen atom, the energies are only dictated by the n quantum number. So 3s, 3p, 3d all have the same energies, okay? Where the energies become degenerate is with a multi-electron atom. And we're going to talk about that and how that reflects here, these wave functions in the next day, okay? Okay, so that's all I'm going to say about the hydrogen atom. And now it's time to move on to helium. Okay. And of course, the Schrodinger equation predicts the binding energies of the electrons to the nucleus in a helium atom also very well. But of course, it is a much more complicated Schrodinger equation. And I'm not even going to write out the Hamiltonian in this case. But I want to show you the wave function here. See the wave function? The wave function is a function of 6 variables. It's a function of 2 r's, 2 distances from the nucleus, 1 for electron 1, 1 for electron 2, 2 thetas, and 2 phi's. Okay, we got 6 variables for the wave function. And the consequence of this is that our solutions for the energies of the binding energies for the electrons in helium or any other atoms are not going to be nice analytical forms. We're no longer going to have E sub n equal minus the Rydberg constant over n squared. If you actually solve for those energies, and you have to do it numerically, if you solve for them, you're going to just get a list of numbers, a table of numbers, but not a nice analytical form. If you solve for the wave function, you're not going to get a nice analytical form for the wave functions like we got for hydrogen. And instead, what you'll get is a value for the amplitude of psi as a function of r, theta, and phi. Okay? All right, but if you get actually much above 3 electrons, it turns out that even numerically, you can't solve the Schrodinger equation exactly. Right? You have to use approximations. And we're going to look at the most basic approximation that is used that works amazingly, works well enough for us to have a framework in which to understand the reactions of these atoms. Okay? And what is that approximation? Well, that approximation is called the 1-electron wave approximation, or the 1-electron orbital approximation. What does that mean? Well, what that means this. I'm going to take my wave function here for the helium atom. This wave function, which strictly is a wave function that is a function of 6 variables, and I'm going to separate it. I'm going to let electron 1 have its own wave function and electron 2 have its own wave function. That's an approximation. In addition, what I'm going to do is that I am going to let the wave function for electron 1 have a hydrogen-like wave function. I'm going to say that it has the 1s wave function, or the psi 100 wave function of a hydrogen atom. And I'm going to let electron 2 have the psi 100 wave function of a hydrogen atom. Or I'm going to write it as 1s of 1 for electron 1 times 1s of 2 for electron 2. Or another shorthand, I'm going to write it as 1s squared. And if I continued on, here it is for lithium. Lithium, the wave function strictly has 9 coordinates. But I'm going to let every one of those electrons in the one electron wave approximation have its own wave function. And I'm going to let electron 1 have a wave function that looks like a hydrogen atom wave function. The 1s wave function, same thing with electron 2. And then I'm going to let electron 3 have the 2s wave function of a hydrogen atom. And in simplified notation, that's just 1s squared, 2s. And here's beryllium, 16 variables. But I'm going to let every electron have its own wave function. And I'm going to give electron 1 the 1s wave function, electron 2 the 1s, electron 3 the 2s, electron 4 the 2s. Hey, I can also write that, as you've already done, 1s2, 2s2. And I can keep going. And these electron configurations that you've been writing down in high school, that's what they are, electron configurations. Well, they're nothing other than our shorthand notation for the electron wave functions within this one electron wave approximation. That's what those were that you were writing down. Those were our shorthand notation for the wave functions in Schrodinger's equation within this one electron wave approximation. Okay? Now, one thing you do notice is that I didn't, in the case of boron here, let all 5 electrons be in the 1s state, or let all 5 electrons be represented by a 1s hydrogen atom wave function. I didn't because of a quantity that you already know about called spin. Right? You already know that if you're going to put electrons in the 1s state here, that one electron has to go in with spin up and the other spin down. In the 2s, one up, spin up and spin down, et cetera, et cetera. Okay. So what is this quantity, or what is this phenomena called spin? Well, spin is entirely a quantum mechanical phenomena. There's no correct classical analogy to spin. Spin is intrinsic angular momentum. It is angular momentum that is just part of a particle, such as an electron. Okay? The spin quantum numbers actually come from solving the relativistic Schrodinger equation, which we didn't even write down. All right? When you solve the relativistic Schrodinger equation, out drops a 4th quantum number. That 4th quantum number we're going to call m sub s. And we find that m sub s has 2 allowed values. One of those values is 1/2, and the other is minus 1/2. So here we've got a case where the quantum number is not an integer. It's 1/2 and it's minus 1/2. Now, if it helps you to think about the electron spinning around its own axis, like I depict here, well, if that's the case, then the angular momentum quantum number is perpendicular here to this plane in which it's rotating. And you might want to call that spin up. And of course, if it's spinning in the other direction, well, then the angular momentum vector is pointed in the opposite direction. You might want to call this spin down. Okay? If it helps for you to think about this, okay. But remember that this is not correct. This is a classical analogy that we're trying to draw here. We're trying to say that this electron is rotating around its own axis. That's not true. Right? This angular momentum is just an intrinsic part That's the intrinsic nature of a particle such as an electron. And next time, I'll tell you about Uhlenbeck and Houchschmidt. See you Wednesday.